Outside-of-the-box thinking and controversy often go hand in hand. New thinking on subjects such as astrobiology, a branch of science controversial in itself due to it being a science with no known examples of astrobiology to study, can often spark controversy because we really don't know what the rules are for such things. Are alien civilizations and technology common? Are they exceedingly rare? Would we recognize it if we saw it? No one knows, yet. And the case can be made that we won't know what an alien civilization looks like until we actually see one. Until then, it's ultimately all just speculation. But it must be discussed and looked for. This is, after all, one of the most profound questions facing the human species. Are we alone? Answering that is a goal of astrobiology. But given our own existence as a civilization of intelligent life, what shouldn't be surprising is if we do eventually see others. So the question is, what do we look for? Which is a specialty of my guest. Most recently, he sparked some controversy in a proposal that the interstellar asteroid OUMUAMUA could conceivably have artificial origins. This is not to say that it does, only that it's a possibility. This has since been followed up with discoveries and papers that are painting OUMUAMUA in an even more bizarre light. Whatever OUMUAMUA is, natural object or otherwise, it's fast taking its place as one of the strangest things we've ever seen in space.
Welcome to Event Horizon with John Michael Gaudier. Joining John on today's program is theoretical physicist Dr. Avi Loeb, the Frank B. Burr Jr. Professor of Science at Harvard University. Dr. Loeb has authored over 600 papers. He is the founding director of Harvard's Black Hole Initiative and also serves on the advisory committee for the Breakthrough Starshot Initiative. In 2012, Time magazine selected Loeb as one of the 25 most influential people in space.
Dr. Loeb, welcome back to the program.
My pleasure.
Now, Doctor, you've been in the news recently regarding the first interstellar object we've discovered, OUMUAMUA. And in particular, you wrote a piece about 6 strange aspects of OUMUAMUA, 6 strange facts. And I wanted to dig into these. The first of them is that there should be either a lot of these objects passing through the solar system at any given time, or they should be very scarce. Do you think, what is your feeling? Do you think they would be, we should not have caught this object, or we shouldn't have seen it, or should these things be everywhere?
Well, about a decade ago, I wrote together with 2 collaborators the very first paper to forecast how many asteroids should we find in the solar system that came from outside of it. And we did the calculation based on what we know about the solar system, and we predicted that surveys like Pan-STARRS would not find anything. So we were off by somewhere between 2 to 8 orders of magnitude, a factor of 100 to 100 million. We thought that there should be far fewer objects than necessary to explain OUMUAMUA. So the fact that we detected it, first of all, tells us that this population of objects is much more abundant than we expected. Now the question is, where do they come from? And if you go through the numbers, you find that if OUMUAMUA is one out of a population of objects on random trajectories that are filling interstellar space, then there should be of order 1 such object per volume occupied by the Earth's orbit around the Sun. So this is quite a large abundance. There should be 10 to the power 15 of them right now within the Oort cloud of the solar system, so within the outer boundary of the solar system. And another way to put it is there should be 10 to the power 15 of these objects, 1,000 trillion objects produced per star over the age of the Milky Way galaxy. And that's a lot of objects, much more than we expected. And so the actual existence of Oumuamua by itself is already a surprise. But then this number of objects, of course, is reduced dramatically if you were to contemplate the possibility that it has an artificial origin, because then if it's a probe, for example, it may follow a very special trajectory targeting the core of the solar system, the habitable region where life may exist. In that case, objects on plunging orbits would account for Oumuamua, and there would be far fewer, by a factor of around 30 million. Less than the 10 to the power 15 that I mentioned before. So the large number is if you assume that it's one out of a population of random objects. And then, the question is it natural or artificial as to whether this assumption is correct or not.
Now, Doctor, you also say in the paper that the Oumuamua occupies a very strange frame of reference, or at least a unique frame of reference within the galaxy. What do you mean by that?
Well, it so happens that the object started at rest relative to the so-called local standard of rest, which is the frame of reference obtained by averaging the motion of all the stars in the vicinity of the sun. So stars are moving relative to each other, and if you take the average of all these motions in the neighborhood of the sun, you get to the local standard of rest. And that's the galactic frame of reference, so to speak. And it so happens that Oumuamua was at rest in that frame. Only 1 in 500 stars are so slow as Oumuamua was before it entered the solar system. And so one way to think of it is that Oumuamua resembled a buoy on the surface of an ocean that sits still on the surface until a boat comes over and kicks it. And so the solar system bumped into Oumuamua just like a boat bumps into a buoy on the surface of an ocean. And the relative speed between Oumuamua and us is simply a result of us moving towards it. This is rather peculiar because if it originated from planetary systems like the solar system, then you would expect it to inherit the motion of the parent star and move at about 20 kilometers per second relative to the local standard of rest. We don't see that. It seems to be associated with this preferred frame of reference. And one possible interpretation is that there is a network of such objects in the galactic frame, and they serve as some road posts, and stars run into them every now and then, like the solar system ran into Oumuamua. Of course, we don't really know, and we have to wait for the second object to be discovered. If the second one is also at that frame of reference, it would make the likelihood of a random event of this type to be 1 over 500 squared, extremely small probability, almost 1 in a million. And so I would say that we just have to wait, and if there is another one coming at the same speed from the same direction, it would look really peculiar.
It would indeed. Now, what natural process could produce this? Would this, if it is natural that produces frame of reference, would that simply indicate that Oumuamua has just been out circling the galaxy for a very, very long time?
No, because there is no process that can slow down objects to exactly the local standard of rest. In fact, after the interaction with the sun, Oumuamua is not in that frame anymore because it was kicked around. You can think of the buoy analogy. Once a ship runs into it, it sets it in motion, and the buoy is not at rest anymore. And so the same thing happened to Oumuamua. Once it was kicked by the sun, it's not at rest anymore in that frame. And so most of the time, objects get kicked to roughly the speed of stars in that frame of reference. And it's very difficult to keep them at rest. Only 1 in 500 stars is so slow, and so the chance of it originating from a star that happened to be slow is quite small. Moreover, if you think about the other planetary systems, most of the objects that are ripped apart from their parent systems originate from the outer parts of these systems, like the Oort cloud, because they are the most loosely bound rocks in a planetary system. So the Oort cloud has objects that, with a very small nudge, can be ripped apart from it. Less than a kilometer per second kick would rip them apart from the solar system. And so you would expect most of the objects to originate from the outer parts of planetary systems, and there they have they basically inherit the speed of the host star, because to kick them out of the system you need a very small kick. If you want an object to be ejected from the inner region of a planetary system, you need to provide it with a much stronger kick. And moreover, in order for it to be in the local standard of rest, it needs to have a kick exactly in the opposite direction to the motion of the star, the parent star, so that the two speeds will cancel out each other and the object will end up at rest in the local standard of rest. So the likelihood of that happening is very small. And it's simply peculiar to see the first object not only belonging to a population that is much more abundant than we expected, but also being at rest in this special frame of reference.
Say we look at astrobiological possibilities for OUMUAMUA. What would the advantage be to putting it in that frame of reference?
Well, it depends on its purpose. And one can imagine such objects being serving as road posts, as defining the galactic frame of reference locally. One can imagine them as staying still in that frame and letting stars run into them. And then, of course, perhaps even probing the inner regions, the habitable regions of planetary systems once they enter into it. It's not at all clear. It all depends on what the design of this artificial object might be. And it's sort of like for us, it could serve as a message in a bottle in a way that was swept to our shore. It could be a technological equipment that we happen to find, and the meaning of it is yet to be identified. And of course, it's interesting to contemplate this possibility, because if it does belong to some alien technology, we might realize that we are not the smartest kid on the block, that there is someone else out there that is outsmarting us.
One could say, you could draw the analogy to Earth, in that someone from 1,000 years ago would not have been able to predict what a cell phone would be.
Exactly. And so we can only imagine things that we have seen. And so our imagination of what might be out there depends on how advanced our technology is. We only have a couple of centuries of technological development. And we cannot really imagine what our technology would be like 1,000 years from now, 1,000,000 years from now. And of course, the universe is 10 billion years old. So think about how much more advanced the technology might be.
Now, if OUMUAMUA wasn't strange enough, it presents us other very unique attributes, particularly its shape, which seems to be unique compared to anything in the solar system that we've seen. What are some of the possible shapes that OUMUAMUA could be?
Right. So what we know is that its brightness changed by a factor of 10 as it spun around. So it rotated over a period of 8 hours. And we've seen a number of these rotations of OUMUAMUA. There are detailed observations over a period of about 5 days. I wish the observers continued to monitor it over a month, because then we would figure out its geometry much better. But whatever they provided us with is sufficient to infer that, if it has had a constant reflectance or albedo, then it must have been 10 times longer than it was wide, projected on the sky. Now, even if you take a piece of paper that is extremely thin and put it at some random orientation in front of you, you will never see it precisely edge on. Most of the time you would see it at some angle, and you would an axis ratio projected of 10 to 1 does not mean that the object has a finite thickness. It could be extremely thin. In fact, if you analyze the light curve, the brightness of the object as a function of time, as it was spinning, you would conclude that probably if it has a constant albedo, it was much more extreme in shape than 1 to 10, probably 1 to several tens. And, that's very extreme because for solar system asteroids or comets, the most that we have seen in terms of changes in brightness is 1 to 3 or so. And so we're talking about an order of magnitude, a factor of 10 more extreme in shape than we are used to. And so the question is, what is this shape? And an analysis of the tumbling motion of this object implied that it could be one of two likely shapes. If it is in a very excited state of tumbling, the kind of state that you expect from a lot of kicks along its tumultuous journey, then it should be pancake-like. And if it, on the other hand, if it suffered very few kicks and it's sort of at the least excited state in terms of its tumbling, then it's most likely to be a cigar-shaped object. Now, if you look at all the artist illustrations that appeared online, they mostly refer to the cigar-shaped object. However, I would find the pancake-shaped configuration much more likely, because it's quite likely that this object suffered a lot of kicks along its lengthy journey. And so that's interesting by itself, that based on its tumbling motion, if you assume that it's in the most excited state because of the many kicks that it suffered, then it should be a pancake-like geometry, very extreme shape, without any reference to the possibility that it's a sail. That already sounds very exotic.
Now, this very fast tumbling, this rotation that it exhibits, how does this relate to the local standard of rest, that it seems to be sitting there in one aspect, but it seems to be highly excited in another? How do those two relate?
Well, the motion relative to the local standard of rest is of the object as a whole. The tumbling motion is, if you go to the frame of the object spins around. And so that's a completely different type of motion that is a result of the fact that, one end of the object felt a slightly different force than the other end. And you can get that when the object passes near stars or when dust or gas is scooped by the object. So one end might not be exactly feeling the same force as the other end, and as a result, the object will tumble or spin around. But that motion around some axis has nothing to do with the overall motion of the object relative to the local standard of rest. These are two separate things. And in fact, the spinning motion has a period of 8 hours, a very short period. So when you monitor the motion of the object, for example, in the sky, you can average over the spin of the object around its axis, because it takes only 8 hours and it takes months it took months for OUMUAMUA to pass in our vicinity, and it takes thousands of years for it to cross the Kuiper belt, and eventually even longer to cross the entire solar system. So these are two different quantities, the spin of the object compared to its motion in space.
Now, recently, a paper came out based on observations, or actually non-observations, from the Spitzer Space Telescope. It looked for OUMUAMUA and simply didn't see it, implying that OUMUAMUA must be very small, and for us to have seen it at all, it must be very shiny, bright surfaces. It also failed to detect things like carbon dioxide, which is what you would expect if it were a comet. What does all of this say about OUMUAMUA?
Yeah, that's very interesting. This report came about a week or so after our paper was published in the Astrophysical Journal. So I didn't know about it when we wrote a paper about the possibility that OUMUAMUA is a light sail. And it's fully consistent. The results that were reported from Spitzer are fully consistent with our original proposal. Basically, Spitzer did not detect anything. The Spitzer Space Telescope looked at OUMUAMUA but didn't see anything. And that means that it didn't see any heat emitted, infrared radiation emitted by the object as it passed in the vicinity of the Earth. And that, since we know the trajectory of the object, we know its surface temperature. It was heated by sunlight and reached a certain temperature on its surface. We can calculate that temperature, and the fact that we don't see any heat emitted from it with the Spitzer Space Telescope sets an upper limit on the size of the object. We know the temperature of the surface, so we can set a limit on the area of the surface that is emitting from the fact that we haven't seen any emission. And that upper limit on the size is of order 100 to 200 meters. And that's smaller than we originally expected based on the typical reflectivity of comets or asteroids. So the fact that the object is smaller than originally expected implies that it must be shinier, because we see a certain amount of sunlight reflected, but now from a smaller surface. So the surface has to be more shiny in order to reflect the same amount of light that we see. In fact, if the object is only 20 meters in size, then it must be a perfect reflector. It must reflect all the sunlight impinging on its surface. If it's 100 meters in size, then it has to reflect about 20%, a fifth of the sunlight shining on it. And that's sort of at the upper end of how shiny solar system objects can be. Asteroids or comets are at most reflecting 20% of the sunlight falling on them. And the typical reflectance is a few percent. So we can already say that this object is unusual in the sense that it's at the upper end of the distribution of reflectance. And it's about 10 times more shiny, at least 10 times more shiny, than a typical asteroid or comet. And of course, that is entirely consistent with the possibility that it may be artificial in origin. Combining that with the unusual shape, the unusual abundance, the unusual velocity, each of these factors is unusual on its own. And when you have so many factors that are unusual, you start wondering, what is this object if it's nothing like an asteroid or a comet that we have seen before? If it's so common, the nursery of such objects must be quite different from the solar system. And irrespective of whether it's natural or artificial, we will definitely learn something new when we find more of the same, more objects like this one. We definitely have the wrong idea about where such objects are produced and how they are produced. And that's exciting because it means that by getting more data on objects like OUMUAMUA, we can learn something new. And it's a whole new way of exploring what may happen in other planetary environments. It's sort of like walking on the beach and looking at seashells that were swept ashore and examining them to learn about their origin. And every now and then, one can find an object that is of artificial origin, like a plastic bottle in which there is a message. But even if it's not artificial, you learn about how these objects are produced. And I think it opens a new window into what happens far away near other stars, without forcing us to develop spacecrafts that will reach that far. So we are relying on the fact that the solar system is scooping up objects as it moves through interstellar space. These objects spend a lot of time on their way to us, and that saves us the time to travel elsewhere.
Okay. So we have two possibilities for a light sail, something that's being affected by radiation pressure. First we'll do the natural. Is there any process that you can think of that can produce a natural light sail in the galaxy? Now, I wonder about things like that because if it's a fragment of a planet, Earth can produce some very, very strange materials like mica, where you can have this very thin sheet of material that might fit the bill. Can you think of any natural process that would produce a natural light sail?
Well, I was trying to think about that, and the farthest I could get is imagining the process of spallation. So when an asteroid impacts on a planet like Mars or the Earth, it could potentially lift the outermost layer of the crust of the planet and create sort of pancake-like piece of rock that flies out. And in fact, people talked about that in the context of panspermia, a process that could deliver life from one planet to another, because we know that rocks from Mars, for example, reach the Earth and presumably vice versa. And if they had life in them, then perhaps life was brought to Earth from Mars. And how can you deliver life? Well, one way to do so is if life exists on the surface of a planet and you lift the outermost layer of the planet without actually heating it much. And there is evidence that one of the rocks that arrived to Earth from Mars was not heated by more than 40 degrees or so in the process from the launch till re-entry. The inner core of the rock was not really heated much. And one way to do that is through spallation. Now, the problem with that is it's hard to imagine it generating something as thin as a millimeter. You expect it to be meters thickness, and moreover, as it gets lifted off this plate of rock, it will presumably break down into pieces that are rounder. And that's why we see most asteroids being at most 1 to 3 in their axis lengths, and we don't see things that are so extreme. And so I simply, the answer is no. I could not think of a method of generating a thin film that will be sturdy enough to survive the journey in interstellar space. And so if it turns out to be such an object, I would argue that it's most likely to be artificial.
And with that, we have to go to a break. I'm joined today by Dr. Avi Loeb of Harvard University. We'll be back in a moment.
John, it is good to be back. Are you settled back into your routine?
I am indeed. It was an interesting few weeks, to say the least.
So you enjoyed your surprise trip to Pirate Adventureland?
I'll admit it. I was surprised, but did you really have to drive the LeBaron that fast? Those numbers on the signs are limits, not targets.
In your car, John, they're achievements.
Did you remove all the modifications, including restoring the LeBaron's original voice?
No, I left it out, John. We all know Erin needs the work.
Did you just... And we're back with Dr. Loeb. Now, Dr. Loeb, I suppose one of the strangest aspects of OUMUAMUA is this odd acceleration that it seems to have as it leaves the solar system. Now, a lot of people are talking about things like a gradual outgassing of maybe pure water vapor or water ice that's pushing this thing. How likely is that?
Well, we haven't seen anything like it in other comets. And what you need is about 1/10 of the mass of OUMUAMUA to evaporate in order to give it the necessary push that was observed. And that is independent of its size. It's simply a matter of momentum conservation. In order to provide it with the extra kick that was inferred observationally, about 10% of its mass needs to evaporate and push it through the rocket effect. And that implies that there should be a lot of gas behind it. Now, how come we haven't seen it? Well, first of all, we haven't seen a cometary tail. That would have been easy to detect because it scatters sunlight, and that's usually due to dust particles. So the Bialy et al. Paper that detected the deviation from an orbit shaped just by the sun's gravity conjectured that maybe the dust particles are bigger than expected, and therefore we can't see them. Because if you have big enough dust grains, they will not reflect sunlight as effectively as small dust grains that have roughly the size of the wavelength of sunlight. And so they argued maybe there are big chunks of big dust particles ejected instead of small ones. The problem with that suggestion is that the Spitzer Space Telescope looked at this object, and it was sensitive, very sensitive, to carbon-based molecules like carbon monoxide or carbon dioxide, which usually accompany the evaporation of ices on the surface of a comet. And it put very tight limits on the evaporation. It didn't see any emission from carbon-based molecules. And so in that paper, again, the conservative observers argued for a more conventional explanation. They said, oh, maybe it's pure water. Maybe you just have water molecules without any carbon-based molecules. But that is hard to believe because usually carbon and oxygen are made in stars in similar quantities. And And whenever you have oxygen, you have also carbon and vice versa. And so it's hard to imagine how you would get water molecules to evaporate off the surface of Oumuamua without carbon-based molecules. In addition, there is an argument that has nothing to do with watching the dust or the gases off the surface of Oumuamua that rules out the possibility of cometary outgassing. And that's based on the fact that all comets that show outgassing change their spin period. So if you have enough thrust to push them through the outgassing, that same thrust is working unevenly across the surface of the object. And as a result, it changes the spin period of the object so that you have these tiny jets pushing on one end of the object stronger than the jets on the other end. And so as the result, the tumbling motion of the object changes and the rotation, the spin period changes. And we see that very often on comets. And there was a paper analyzing what we might have expected Oumuamua to do if its extra push was a result of outgassing, and it would have been easily visible. So the limits we have on the change in the spin period of Oumuamua rules out on its own outgassing at the level required to push it. When we make the analogy with comets, it's clear that a standard cometary outgassing process is not in effect. We don't see the gases, we don't see the dust, and we don't see the change in the spin period. And when you combine all these factors, to me, they imply that there is no cometary activity on this object. Anyone that argues otherwise needs to find or identify another example of a comet where all three factors were somehow circumvented. And, the situation is very similar to what we see, for example, in galaxies. We see stars moving, and they move much faster than we expect. And this is an anomaly. And whenever you have an anomaly in astrophysics, you start wondering what could account for it. And you start with conventional explanations. And so people tried over the years to come up with conventional explanations, and they couldn't. And then the concept of dark matter was invented to accommodate this extra mass that you need in galaxies. So we believe that there is some extra matter that we cannot see, and we call it dark matter. This is a hypothesis. It's not proven. We haven't detected dark matter yet. But the idea, the concept of dark matter is part of the mainstream because there is no conventional explanation other than that to explain a series of anomalies that we see, not just the motion of stars, but also other facts in cosmology. And so it's a standard element of the scientific process that when you are confronted with an anomaly, you try to come up with conventional explanations. But when these explanations have a problem, when you don't see evidence for them, or they contradict some evidence that you find, then you have to come up with more innovative ideas, with more imaginative ideas. And this is part of the scientific process. So I don't see at all why any scientist would be against coming up with a potential artificial origin explanation to this extra push that we see in the case of Oumuamua. Just like in the case of dark matter, I would say dark matter is as imaginative, if not more, than the idea of an extraterrestrial civilization, because the concept of an extraterrestrial civilization is based on two facts. One, that we exist, and second, that the conditions on planets throughout the galaxy are very similar to the conditions on Earth. About a quarter of all the stars in the Milky Way galaxy have a planet of the size of the Earth with a surface temperature similar to the Earth, such that liquid water may flow on its surface and the chemistry of life as we know it would exist. And so there is nothing really speculative about saying that what we find on Earth exists elsewhere where the physical conditions are similar. I see that as a relatively straightforward extrapolation. And so to me, it's a complete mystery as to why the possible existence of another civilization is considered outside the mainstream of astronomy. I don't think it should be. I think it should be as much in the mainstream as the concept of dark matter, if not more, because we know that we exist. We have a proof of principle that a civilization can exist. Now, there are even more imaginative ideas out there. For example, extra dimensions, which are part of the mainstream of particle physics, even though we have no evidence for extra dimensions. And somehow, sociologically, it's well accepted that you can speculate about extra dimensions as a way of unifying quantum mechanics and gravity. So to me, it sounds a bit inappropriate to resist the idea of extraterrestrial civilizations because it's so rooted in facts that we know are true. And therefore, if we have an object that behaves in a peculiar fashion on so many counts, I would not dismiss up front the possibility that it's artificial in origin. And it should be on the table. And many people do is dismiss it up front. They say, oh, my gut feeling is that it's probably natural. The problem with gut feelings is that they are based on past experience. And so if you expect the future to be the same as the past, gut feeling is a good guide. But if you want to allow yourself to make discoveries, you cannot rely on gut feelings. So for example, quantum mechanics was discovered by experiments. And it brought in the concept of action at a distance, which was not very intuitive to the physicists at the time. And in fact, Einstein resisted it. Einstein said, it's spooky action at a distance. I cannot believe that it exists. And he wrote papers arguing that quantum mechanics is misinterpreted and it's in fact predictive. It's not probabilistic. And there were experiments done in the decades that followed Einstein's resistance, and they all demonstrated that he was wrong, that his gut feeling was wrong. So Einstein had the wrong gut feelings. We should learn from that. Galileo, for example, used experimentation to check the gut feeling that we have that heavy objects fall faster than light objects. And he found that they fall at the same rate. Here is another example where experimentation taught us something that our gut feeling did not really forecast. Our gut feeling was that the sun moves around the earth because we see it moving in the sky. And then, again, Galileo argued otherwise. He was put in house arrest. If there would have been Twitter at the time, obviously most of the tweets would have been against him. But that doesn't matter. The sun doesn't move around the earth, irrespective of what Twitter says or what people think. There are facts out there. The nature of Oumuamua is whatever it is. It doesn't matter what we think or what the popular view is on Twitter.
Now, that brings up biases. And of course, anything when one says the word alien, it brings up a bias because on one count, there's a pop cultural sensationalist phenomena regarding aliens, of course, which, doesn't really seem to have any kind of a basis. But there's also, are we alone is one of the most profound questions humanity can ask. So it seems to be something that scientists should want to answer. And to an extent it's done with SETI searches and things like that. But nothing says that, detecting a radio beacon 10 light years away is any different than detecting a probe passing through the solar system. We just don't know what the rules are on such things. And, we would send probes if we could. Now,
right.
One thing that...
Yeah. We are actually contemplating sending technological bottles to other planetary systems. And if we are starting to think about it now, then a civilization that is much older than ours may have done that a long time ago. And so we should be obviously open-minded. And just to finish the point about this peculiar motion of Oumuamua, the deviation from its trajectory, as anticipated based on the sun's gravity, implies that if you want radiation pressure to provide the extra force, and that's the only possible force that I could think of other than outgassing, then you need the object to be very thin, less than 1 millimeter in thickness and more than 20 meters in size. And so that's a thickness that is at least 10,000 times smaller than the size of the object, and it sounds like a sail. And that's what you need in order for the sunlight to push it enough to accommodate the extra push that it exhibited during its orbit. Although the push is only 0.1% of the force, the gravitational force from the sun, it's still very significant. And the object goes in a direction that is quite different from what one would have expected without this force.
Now, the elephant in the room, I suppose, to sort of wrap up the strangeness surrounding this object is its trajectory, which brought it, as I recall, at its closest approach, 0.15 AU from Earth. So it just seems to have picked the interesting planet in the solar system to pass relatively close by. Does that seem strange to you? I mean, what are the odds of that?
Well, that is not necessarily strange because we would have found this object only if it passed close to us. So this may be a selection effect. It all depends on how many such objects exist out there. So for example, we can find out if we develop a telescope that is much more sensitive than pan-stars. And we are actually in the process of doing so. There is the Large Synoptic Survey Telescope, LSST, that will become operational within 3 years. And it will be much more sensitive than pan-stars. And in that case, we could see objects much farther away. And if we find other objects passing farther away, and many more of them, of course, because the chance of that happening is far greater than the chance of an object passing close to the Earth, then we will be assured that there is a large population of such objects. If, on the other hand, we search for a year or two and not find anything, then it would mean that this object was very special. It was on a special trajectory, and it's not a part of a much larger population. And then the only way to find more about it would be to chase it down. And that would require developing a technology that is much better than the chemical rockets we currently have, because the object is moving faster than our spacecrafts. And in principle, it's possible that within a decade or two, we'll develop such a technology and then be able to chase it down. But such a mission would be extremely expensive, more than $1 billion, because we will have to equip the spacecraft with a small telescope such that it can track the fading image of OUMUAMUA. So OUMUAMUA is very peculiar. It's sort of like a guest that came to dinner from the street without us expecting it. And by the time we noticed how weird it was already out the door into the dark street. And by now it's extremely faint, and because it reflects sunlight at a lower level. And in order to track it, we need to equip a spacecraft with a telescope that will monitor where it is and correct the course such that it will approach it.
So if we are barring that, say we can't, we just can't justify going out and looking at it directly with a flyby, is there any ways left to observe OUMUAMUA, or is it just simply too far away now?
It's too far away. It was already too far in January 2018, and now it's a year later. The problem is that it gets dimmer as inversely with the distance to the fourth power, because the amount of sunlight that it intercepts declines as inversely with the distance squared, and then the amount of light that we get back has another factor of 1 over distance squared. And so altogether it's 1 over distance to the fourth. So very quickly it dims down, unless of course it produces its own artificial light, but we haven't detected any. So it seems like this object was already too faint for the Hubble Space Telescope to see it a year ago, and by now it's extremely faint. And so if we wanted to chase it down, we would do so by following the path that it took and extrapolating it and just searching around once we get closer to it, searching around for its image, and then getting even closer and taking an image. But if we don't see additional objects with pan-stars or with LSST, then there would be a seventh peculiar strange fact about OUMUAMUA, the fact that it's rare. And that would also imply that it appeared at a special time. It could still be artificial, and we could still have more of the same, because every few years there is a new object showing up. But if we don't see new objects, if we don't see many more objects when we improve our sensitivity, that would argue that something strange happened on October 19th, 2017. This was a very unique object. And I should say, that one of the problems that I have with claims for UFOs, unidentified flying objects, is that there were reports over the past decades about such objects. And over the past few decades, our technology for detecting objects or images has improved dramatically. We can now see things much fainter than we could have seen several decades ago. And yet, all of these claims are always on the margin of detectability or believability. And that makes them unlikely to be real, because if they were real 30 years ago, we would see very clear evidence for them using present-day equipment. And same should apply for an object like OUMUAMUA. If another one comes along and we have much better instruments looking at it, we would know much more about it.
Now, that's interesting because it brings up ideas like, old ideas like von Neumann probes possibly being in the solar system. And if one happened to dip in the atmosphere and someone saw it, it would be an unidentified flying object. But that always, suffers from, of course, geography. For example, certain countries see UFOs more than other countries and all sorts of things. It suggests that there's nothing there. But do you think there is anything there? I mean, could that be a viable thing to study if it's even possible?
Well, I approach this subject as a scientist, just like I approach the issue of dark matter in galaxies. And the healthy way to approach it is not to have a prejudice, not to have assumptions. The mistakes that are made very often are to assign some likelihood to one outcome or another. And the problem with that is that, if you tell yourself something does not exist, then you never check for it. And then it's a self-fulfilling prophecy. And if you have a very clear agenda when you are taking data, you will not discover new things because you are guided in a very narrow path that you define ahead of time. And that's one of the issues I have with some funding schemes, funding of research, where you are asked to declare ahead of time what you will discover if you are given the grant. And that's a self-contradiction, because the whole idea of doing science is to be open-minded, to find things that you haven't expected. And so the best way to approach, especially a subject as novel as the search for life elsewhere, is without prejudice and as a way of exploration, just trying to collect as much data as possible and not have a prejudice. And whatever the sky teaches us, we will learn, and we will get wiser in that process. And even if OUMUAMUA ends up being natural, as I mentioned before, we will learn something new, because we haven't expected it to have all these properties. And we should be humble in the way we approach nature. We should not believe that we know the truth before we uncover it. And I think the mistake that many people make is out of arrogance. For example, people argue, we might be unique, we might be special. That shows arrogance. I prefer to believe that we are not special, that life exists elsewhere in a way that is similar to what we find here on Earth, or even more sophisticated ways. And the way to find out is just by collecting data. And let's use our best telescopes in the future to find more of the same, more objects like OUMUAMUA. And every object that enters the solar system, we should definitely examine. That should be a new method, a new window into the universe that was not explored so far, because OUMUAMUA was really the very first object to enter the solar system from outer space.
Now, to flip this around, you're intimately involved with Breakthrough Starshot, which essentially the ultimate goal is for human civilization to send out probes to other star systems. Now, this is a proof of concept for now, but what is a time frame for a flyby of another star system with Breakthrough Starshot?
Well, we have to develop the technology. The idea behind Starshot was that we would like a technology that allows us to reach another star within our lifetime. And since I'm 56 years old and the funder of the project, Yuri Milner, is of the same age, we defined the 20 years as the time that we allow for a probe to reach another star, so that we can see it during our lifetime. There are other people involved in the project that are older than us, and they wanted an even faster speed. But if you imagine a probe that could reach the Alpha Centauri system, the nearest star system, within 20 years, you need to provide it with 20% the speed of light, a fifth of the speed of light, because Alpha Centauri is 4 light years away. And so it takes light 4 years to reach us from there. If there is a civilization out there, they don't really know about the elections of 2016 because the signal is halfway to Alpha Centauri right now. It's 4 light years away, so the elections took place 2 years ago, and it's halfway. And so if you want to reach Alpha Centauri in 20 years, you need to launch a spacecraft at a fifth of the speed of light. And when I looked into it, there aren't many technologies that can do that. And the only one that I could identify is pushing a sail with the force of light. Because then you can, in principle, reach the speed of light, and you don't carry the fuel with you. You're not limited by the mass of the fuel that you have to carry with you, as in the case of rockets. And when I recommended this method to Yuri Milner, I told him the situation is quite similar to getting married. You just need one solution to solve your problem, not more than one. And so the fact that we identify one technique is good enough, and we should be happy about it. And so now we are working on developing the technology, demonstrating that indeed one can combine a lot of small lasers into one coherent beam that is very powerful. What one needs is roughly the power used for liftoff of the space shuttle, about 100 gigawatt. During a period of a few minutes. And instead of delivering it to the space shuttle, one needs to deliver it to a single gram of material so that this single gram will reach a fifth of the speed of light. And that can be done because, for example, this single gram of material can include a camera, a navigation device, a communication device. These are the guts of a cell phone, where the electronics is miniaturized already to that level. And one can imagine a sail that is not weighing much more than that has roughly the size of a person. And what you need is to shine a laser beam that is 100 gigawatt in power on this light sail and push it over a few minutes. And the laser beam can be produced on Earth and then go through the atmosphere. And if the sail is released by some other ship above the atmosphere, then it would feel the thrust from the laser and reach a fifth of the speed of light across a distance roughly 5 times the distance to the moon. And so altogether, that was the concept that we came up with. And it faces many challenges, many technological barriers. What we are focusing on right now is demonstrating the laser technology, that we can combine a lot of small laser beams into one powerful coherent beam, and the light sail technology. What we want is to identify materials that have a very good reflectivity, because if only one part in 100,000 of the laser beam gets absorbed in the sail, it will burn it up. And so we need a very good reflector. And so on the one hand, you want material that is a very good reflector. You want the shape of the laser beam to be such, the shape of the sail to be such that it will ride in a stable fashion on the laser beam. So you might think maybe an umbrella shape is the best, but in fact, we calculated that a spherical shape might be even better, sort of like a balloon that is being pushed by a hollow laser beam. That might be a good stable configuration. And we are working on the light sail design and composition at the moment. So we have allocated grants to various research teams, about a dozen of them on the laser beam and about a dozen on the light sail, and to start developing the necessary technologies. And so we are at a very preliminary stage right now, but we have a promise for $100 million for this research and development phase over the next decade from Yuri Milner. And I will not shy away from admitting that the reason I thought about a light sail interpretation of OUMUAMUA was my involvement in this project. And I'm chairing the advisory board for Starshot, and that knowledge of the underlying physics allowed me to consider the possibility of a light sail for OUMUAMUA.
And that was segment 1 of my recent interview with Avi Loeb of Harvard. Part 2 will debut in 2 weeks. But for next week's show, I'll be sitting down with Emily Lakdawalla for a discussion of solar system geology. See you next week.